started. So, hello everyone, this is the sixth journal club. The sixth journal club about Entangled Tardigrades from Ricky. And well, Ricky, you can start this presentation. This meeting is
Hello everyone. As Alberto said, this is the sixth journal club, and we're looking at a paper about entangling tardigrades or water bears, and this is the paper title. So it's entanglement between superconducting cubits and a tardigrade, and what they wanted to see is a quote on the bottom from the paper. It studies the possibility of quantum effects in biologically relevant processes, but is also concerned with quantum features of entire organisms. So they try to take the smallest kind of living organism possible, not the exact smallest, but one of the smallest, and see if they can apply quantum effects to it. And these the people that participate in this paper actually also a few years ago won the what is the Ab Nobel or Ib Nobel prize. So it's kind of like the prize for the most crazy scientific paper. And yeah, so I wanted to start with what a tardigrade was. So usually they come between 0.3 and 0.5 millimeters, but some of them can get up to 1.5 millimeters, and they're found literally everywhere on Earth. The tardigrades they actually use in this paper, or they found it on the top of a building in Denmark. So the researchers just went to the top of their building and scooped up a few. And another reason why they wanted to use tardigrades instead of a virus or anything like that is because they can achieve something called cryptobiosis, which is when they suspend their metabolism by dropping their water content down to way below 1%. So as can you see my cursor? No?
I see your mouse. It's top and round.
Yeah, so the active form, so just the normal form is this kind of bug-looking thingy. When it's hydrated, so when it has its full water content, and when it loses its water content is when it's known as the ton state. It looks like this. So it shrivels up completely. And in this state, when they just have no water content, nothing, they can achieve, they can survive in super insane conditions. So near vacuum, really high pressures, really low temperatures. But I think there's a caveat with how high of a temperature they can survive. And they kind of come in a variety of forms. So this one over here has armor on it, and with spikes, and I think that's really cool. So I included that. And before we actually get into the paper, I wanted to talk about the structure of a transmon qubit. So what they try to put the tardigrade into, or what they're trying to entangle the tardigrade to. And so in this, so transmon qubit, we have the aluminum cavity here with input-output signals, and very tiny in the middle of this, you have these two pretty much capacitors, and in between here, so you can kind of see it a little bit better on this part. We zoom in to to between here, and you have the Josephson junctions. So this is kind of so this is so you have the superconductor on top of a insulator. I think it's an insulator, and this can achieve and this has a lot of different quantum effects where it allows for a certain tunneling and creates this potential well where we can have different energy levels to hop around so that we can get some kind of computational effect. And so I just wanted to point this out because the paper's a little confusing in where they put the tardigrades. So so if I go to the next one. So the tardigrades put in the capacitor in a way, which is this structure, these two black squares, are a little bit different than this, in that I think there's the two levels of the in between the capacitor, or down here. So these two are the different qubits, and then you have the tardigrade in between it. So between this top plate and bottom plate, they stuck this tardigrade, and then also there's the Joseph junction between these two plates, and it is a little weird to see that. And then this capacitor here is this tiny little slit that's connecting these two. Also, I don't exactly know what this black line here is. Maybe that's just the position of the tardigrade. They had some kind of filter paper to move the tardigrade on as well, but they don't show it in any of their diagrams. So I'm just going to assume that this black line is the filter paper. Yeah, so the experimental setup in total, they did 3 different experiments with 3 different tardigrades, and the smallest one was 50, and the largest one was 1,200 micrometers, and then there was one somewhere in between there, and they put them all in the ton state. And in this, so this one's actually the tardigrade in this picture is actually not in the ton state. It's the full tardigrade, but they placed the tardigrade between these shunt capacitor plates, so kind of between this top plate and bottom plate, and that shifted the frequency of the qubit it was placed in. So on the frequency on qubit B went from 3.271 gigahertz to 3.263, which is a shift about 8 megahertz. And in their simulations, they found that the tardigrade had a dielectric constant about 4. Yeah, so the main shift in this was because of the change in dielectric constant that was between the capacitor plates on one of the qubits. And to verify the entanglement, and then they from the system they ran a few experiments. They put some microwaves in there using a protocol called SWIPHT, which I'll also explain later, and tomography, which is a little bit weird term in this, but tomography is just you measure your system, pretty much. Or like you measure shots in the system. If you're familiar with quantum computing algorithms, or not just algorithms, but Qiskit and stuff like that, you put the amount of shots. Those amount of shots kind of are lined up like this, like in an area, and then the average is kind of where the ideal position is supposed to be. And so what tomography is in that case is that you have this amount of shots, and then you map those shots and you kind of reverse engineer the wave function. So you push in some unknown wave function, you get your measurements, you get the shots and where they are, and from there you recreate the wave function. And so if you put just like measurement nodes here and just measure them and then recreate the wave function that was inputted, then you get what's known as tomography. And then I wanted to explain SWIFT a little bit, because they wrote this really long name for it. So speeding up waveforms by inducing phases to harmful transitions protocol. I didn't really know what that was at the beginning. So I read the paper that it was based on a little bit, and all these numbers, I have some citations at the end if you want to look at them. But what this is that they engineer microwaves that they send into the system to avoid harmful transitions. And these harmful transitions are like certain frequencies will not have the desired effect that you want at the end. So what they do is that they kind of just avoid those frequencies or avoid those transitions by either driving or incorporating those harmful transitions into the dynamics. And so what that kind of ends up being is that you have like holes or peaks, or like slight dips or peaks in your wave function, and then from there you send those microwave pulses into your system, and you pretty much avoid a certain amount of errors that you have. So it's kind of like quantum error correction in a way. And so the result of these experiments, so if you just have some kind of 2-qubit system in Qiskit or something, and you just say, okay, I want to measure my entangled system. So you have your Hadamard gate and your CNOT gate. If you're familiar with that, that will give you that'll give you a matrix, or that'll give you an output of where both states have a 50-50 chance of occurring. And so I guess this isn't really explained that well right now, but E is your excited state and G is your ground state. And so what they want to do is try to figure out the probability of going into the excited state and the probability of going to the ground state. And so this lines up where you have 0E, 1G, 0E, state 0E, 1G, and then 1G, 1G. And those are all roughly 50% in the experiment. And you have some kind of imaginary part because you also have to incorporate that, or you have to also know what your imaginary part is, because that shows you some kind of errors in your system. And I wanted to get to like the theory part, or like how they simulated it versus how they experimentally found it. So yeah, they created a model to verify the entanglement, and that model consisted of assuming that the tardigrade was a collection of n harmonic oscillators with and they just didn't know if they had the same frequency or different, so they just assumed that they were kind of all different, potentially different frequencies. And so in this case, you have your the ground state of your qubit, I think. Yeah, so your initial Hamiltonian, or your unperturbed Hamiltonian, is the ground state of your qubit plus the summation of just all harmonic oscillators in your system, where you have your creation and your annihilation operators, or your raising or lowering operations, and some kind of frequency. And then they also then used a perturbed Hamiltonian, this, to figure out what the frequency gap between the excited state and the ground state was. And so in perturbation theory, you just have some kind of Hamiltonian where you have your non-perturbed and your perturbed Hamiltonian, and you add that together and you solve just the Schrodinger's equation. And they're able to find the frequency gap based on just second order perturbation theory. And did I want to explain anything else here? No, it doesn't seem like it. Okay, so this might be like a little weird, just to throw in here. So they defined it like they defined the form of the first excited state here. So like like what the energy was of that state, or like the state in which you have your first excited state. This is actually, I think it's derived from just the normal block sphere representation of a qubit state. And so you have just some excited state, and you have the cosine theta over 2, sine theta over 2. So those are rotations along the block sphere. And typically there's supposed to be a 0 and a 1 here, but they use 1 and 0. This is 0 dot dot 0 is the amount of harmonic oscillators in the system. So this goes n zeros long, and that's the amount of harmonic oscillators in your tardigrade. And then your phi 1 here is actually some kind of what's that term? Some kind of constant here with with the excited state being in the harmonic oscillator's excited state. So yeah, something like that. So you have it like, okay, you have your harmonic oscillator in that state, and so you have the 1 instead of just the 0, and then that goes n harmonic oscillators. And then this cosine theta over 2 they derived as this, which I think is, which I'm not exactly sure because they didn't fully explain how they found this in the paper, but they, but this is very similar to the frequency gap in the theory, and so I would say that they somehow found it through there. And then and then those you can just plug into this, and then that's your excited state. From this, they were able, so the ideal state that they wanted is this, where they have the 1 over root 2 to have it normalized, and then your 2 different states. So you want it to be, so you have your ground state and your excited state, and then 0 and 1. Yeah, and so you have like equal probabilities that it's going to be in the excited state or it's going to be in the ground state, which then, if these are like the theory, that this is the simulated percentages. So I think these are all about 50%, maybe 25%, but these correspond pretty well to the experiment. Kind of what the key takeaway, oh, the fonts are different, but so this led to a fidelity of 82%. So this is fairly certain that the amount of harmonic oscillators in the qubit or in the tardigrade are entangled with the qubit, A. So, and then here's a nice graph. So we still have a theta dependence in our system because of this sine theta over 2. And so when they plotted it out, they were able to see that the percent, so this is the percent of entanglement, that the n, or so the qubit A to qubit beta with tardigrade is almost at 50%. So almost fully entangled. And the rest of these are the tardigrade itself to qubit AB, the qubit A to tardigrade, and then B to tardigrade, and then pi entangle is just kind of like a control, and they map that all out here. And so the other main takeaways of this were they exposed the tardigrade in the ton state to such high, significantly higher extremes than what was previously known for tardigrades. So so in our qubit system, you have to have temperatures of like 10 Kelvin, maybe even below that, and with very low temperature pressures as well. And so these two variables are like the lowest that a ton state was able to achieve. And out of all 3 tardigrades that they used, one of them actually was able to live out of this after the experiment. So they're entangled with a qubit, and then they came out of the ton state and survived. Was funny, and why a few people thought that this paper was like a meme or something was because that they revived they revived after the experiment in 420 hours. So that was a very funny part at the very beginning of the paper. And yeah, and it also shows that the cryptobiosis is a complete suspension of biological processes. So like nothing is actually occurring, and there's no proteins moving around. There's nothing. Everything is just still. Everything is pretty much like not moving. And yeah, but there's still some debate about this paper and whether the biological system, or if biological systems can be entangled, because what they assume, because if you just stick a tardigrade in a capacitor and then you like send some signals through it, are you really entangling the entire system? Or is it just you're just changing the dielectric constant? And it's kind of iffy in that sense. So yeah, and that was that was pretty much like the whole paper. I used a few sources, some images and stuff, if you want to check that out. And yeah, what do you guys think? Do you think the tardigrade was entangled as a full biological system, or do you think it just changed the dielectric constant? Thanks. That's the presentation.
Thanks a lot, Ricky. So if anyone has any question about the presentation or the paper, it's time. If you want to open your microphone or write in the chat, it's okay. The important thing is clarify the question or start a discussion. So, anyone?
I can go back a few slides if you need to.
We'll discuss about the presentation, yeah.
Yeah.
Oh, one from Babika. Can you please share the slides on Discord, Ricky?
Yes. Like, do you want me to screen share on Discord, or would you like to just the whole presentation?
I would like the whole presentation.
Okay, let me throw that
Thank
in
you.
here.
By the way, the armored tardigrades were pretty cool.
Thank you. Thank you. Let me see. Where did I put the presentation?
Anything else? That's another.
Yeah. Is there anything like confusing? Because sometimes my explanations about some things can be a little all over the place.
Oh, it was really exciting. Do you think we could go slide by slide and then ask questions from there? Because I think I had a lot of questions throughout.
But I don't know if you guys had any questions about the tardigrade itself.
Yeah, I think one question I had is that the tardigrade is in the ton state. So what is what is the other state of the ton state? What is the other state of the tardigrade? And
I don't know, the non-ton state or just the alive state? Because the ton state's kind of like it's almost dead. It's like just barely dead. Well, yeah, just the not like alive form, I guess, or just the natural form. I don't think there's another like term for that in a way. And
does this ton state of the tardigrade, did they observe the tardigrade in the system in the non-ton state?
No, they observed the tardigrade in the ton state, so they shrank it down to that shriveled form, and then they put it into the system. This picture here is when they tried to revived it again, while it was still kind of in the system, I think. But this is the fully alive form. And then this is the ton state, where it's just like a little raisin.
If you had like just any dielectric and you used it you just approximated it as harmonic oscillators, would the experiment mathematically have been this same?
I think so. If you put any I mean, it looks like a raisin, but if you put a literal raisin, I think it would be mathematically the same. as well. I think they made a comment in the paper saying that the dielectric constant of the tardigrade was like on the lower side or like at the lower end, and maybe if you had like a significantly higher dielectric constant, it might have not worked, because then like you wouldn't have the electrons flowing through as much or something, or what. But potentially, I think anything could be modeled as just a big collection of harmonic oscillators. I mean, there's that whole debate about if everything is made out of spin or if it's made out of harmonic oscillators.
Can we try to entangle some other organism, microorganism, or in the same system?
Yes, I think the issue then becomes how big it can be, because you have to have it fit at least within the capacitor, I think. Otherwise, it would just kind of be, right? It has to be like at least like a certain size of capacitor, and if you have just a human, like that capacitor would be massive, like because you can't just like put a human between two different like capacitor plates and expect it to be entangled.
Maybe a piece of a human.
Yeah.
Thank you.
Like a human cell or something. If you completely froze it and then were able to like revive it in a way, then you could probably have the same outcome of this as this. Maybe like a neuron or something would be pretty easy to tell if it's alive afterwards.
Okay, thank you. By the way, a very silly question, but like, why are we like entangling tardigrades?
That's the main goal of this was to figure out if how close to entanglement we can get biological systems to. And tardigrades, because of their ability to go into cryptobiosis, they were a pretty good candidate for that. So they went like, because we don't really have room temperature superconductors yet, we have to put qubits at like 10 Kelvin, and not very many things can live past 10 Kelvin, or like even that, like at that low of a temperature. So tardigrades tun state was a perfect example of this. I don't even think viruses can live below 10 Kelvin, if I'm mistaken. But a tardigrade can, and now we know it. So I think Chloe had one in the chat.
Ricky, you had another question in the chat from
I'm reading that. Yeah, it's I mean, like, it is kind of like a hard question to like exactly answer. I mean, we hear, like, we see in like TV and stuff, all like certain scientific questions, like, oh, we want to achieve teleportation and stuff. And I mean, quantum mechanics is one of the best ways to, or one of the probably only ways to kind of achieve that. And to see whether biological systems, even if they weren't like fully entangled, if their system as a whole can kind of be entangled, or if the parts of the system can be entangled with something else, is kind of the point. I mean, usually we have we're just entangling waves, or frequencies, or not waves, frequencies, but like radio waves or something, or microwaves. And a lot of the scientific development at the moment is trying to entangle other things. So earlier last year, they entangled the vibrations of a drum. So like you know how your speaker has like that little like film on the top. When you send like waves through it, it kind of like vibrates. They entangled those vibrations with a qubit's frequency microwave vibrations. So yeah, they want to like expand that and try to like now entangle other things together to see if if we can only entangle waves, or if we can entangle like systems as a whole. And yes, if we assume everything is a harmonic oscillator, we can technically entangle everything, and it's just a matter of if it can survive in the end. But yeah, I guess they just did it for science. I don't know. But it's in this case, I wanted to present it just because it was a funny paper overall.
Could you point out how to match up this experimental setup with the previous slide?
Oh, just like to re-explain this. So when I was like looking at this paper initially, I couldn't really tell what they were doing with tardigrade. Like, are they putting it in the capacitor, and where is the capacitor and stuff like that? So they point out that these two plates are the qubit A and B, but in this case, these two plates aren't the qubit A and B. This is one qubit, and this is like the capacitor. So like this is like an input capacitor, and this is another, or these two plates as a system are the capacitor, or at least this like tiny part in between them is. And it's like, okay, are we sticking the tardigrade in between here? But it kind of seems like it's going out of it. And so what I came to the conclusion of this is that these two plates, or like this black square and the black square underneath it, are these two plates. And somewhere in between there you have like this Josephson junction. And then you stick the tardigrade kind of near it, where it's going to be in between these two black plates, so like in this like white space in a way, where it's kind of going to be influenced by the Josephson junction. And that kind of seems like what's happening here. Does that like make sense? Or am I missing something? No, okay. Yeah. But like just from the paper alone, it's really hard to tell where this tardigrade really is. But I think this like diagram here kind of just shows it as good as possible, without kind of like trying to figure out this experimental setup.
What is a shunt capacitor, as opposed to the capacitor in the previous slide?
So shunt capacitors, I think, are just capacitors in parallel versus series, which is a weird way to put it. But everything I found about shunt capacitors are just about putting them in parallel, or yeah, in parallel. So in this system, so you have like these three capacitors in parallel, and then you just have like loops around the Josephson junctions. Yeah, it's a weird term that didn't fully make sense in that case, because a capacitor is made out of two plates, and why would you need to differentiate a shunt capacitor versus a normal capacitor? It might just be one plate, because usually capacitors have a few different kinds of plates in like the ones you like see in normal circuit diagrams. And this might just be like you have one gap and nothing in between it or something.
I think it's the use of the capacitor, in that you're putting the capacitor in parallel with the Josephson junction, so that's why it's called a shunt capacitor.
Yeah, it seems like that. Yeah.
So, could you go back to the previous slide? Sorry, I'm asking a question.
No, you're good.
So, what's a qubit would be the bottom leftmost diagram?
This.
Which is that whole thing the qubit?
Yeah. So like
Okay.
normally you see qubits like this. So you just have in parallel the Josephson junction and the capacitor, or I guess the shunt capacitor in this case. But so this paper or these diagrams are from the Quantum Materials Roadmap 2021. If you're familiar with that document. And this is kind of how they describe a transmon qubit, and this is from some other kind of paper. And they kind of have the same Josephson junction layout, but if we just consider this entire part as one big X, then yeah, this is the diagram for the qubit.
What is the effect of having multiple Josephson junctions?
That I am not 100% sure of. They're not familiar with yet. It's probably for like error correction or to get like a better signal, but I'm not sure. No, yeah, you're right, Chloe. Like it's not like a typical paper, as in it just kind of like runs through everything, and it doesn't have like, oh, here's the conclusion section and here's the theory section. It's like structured that way, but not like it's like discretely structured that way and not directly structured that way. But yeah, no, it was this one was a little harder to read in all honesty. Like I was also having trouble like following along, like, so what did they mean by this, and like, is this what they mean? And there's a lot of background like knowledge you have to look up in order to actually understand it. Like I like with SWIFT, I had no idea what this was at first. I'm like, okay, I have to like look that up and explain this, because it's just like thrown in there and it's like, oh yeah, you should know this. It's like, no, you shouldn't. But it's just, if they just wrote like error correction, we use error correction to get a better frequency using SWIFT, then it probably would have made more sense.
I think the term would be noise mitigation, I guess.
Well, I don't know if it's noise in that sense. They use harmful transitions. Maybe that is noise. Oh, whoops. Yeah, like I looked
that's
up
just for the acronym.
Yeah, that's probably for because they don't really describe what harmful transitions are, but I guess if you have a noise, then it kind of like noise is harmful for microwaves. So yeah, probably that too. So yeah, do we want to take a poll? Does how many people think that they actually entangled a tardigrade versus how many people don't think they actually entangled one? So I guess we'll do like 1 in chat if they entangled the tardigrade, like actually, and 2 if they did not entangle it, and this is just kind of like BS.
I don't understand how they measured the tardigrade.
They didn't measure the tardigrade itself. They just stuck it in a capacitor and just measured the input and output, or just measured the output of it what this state was in the end. It's a little weird. Let's see, what did I? Yeah, so they like just in essence put a tardigrade in this ton state within a qubit, created a input wave, an input microwave with SWIFT that's that has kind of this input, so kind of like an entangled input, I think, and then measured the tomography at the end to see what the wave what it evolves into. Yeah, that. Or in their like explanation, they wanted this state. Okay, we got 1-1. So one person actually thinks that they entangled the tardigrade. Nice. Oh wait. Wait, Leah, I think one of them should be I think it should be like this. Now you're 50-50. You think that's you're in superposition between option 1 and 2? Anybody else have an opinion on this? All right, cool. I would probably say no, but they didn't entangle it. But yeah, I think it's an interesting topic regardless. All right, okay. Do we want to, if there's no further questions, we can end it here.